Today, we're going to be talking about strong acid, strong base titrations. First off, a titration is going to be using a acid or base of known concentration to determine the concentration of an unknown acid or base. So let's go ahead and get started. First things first, the purpose of a titration. So when we're looking at titrations, our whole goal is to determine the concentration of an acid or base. Acid or base. And in order to do this, we must know the concentration of the base or the acid that we're using to titrate the acid or base with. This is probably the most common type of titration that we're going to be looking at, but know that when we're looking at weak acid-base titrations, we can also use these processes to determine the equilibrium constant for a weak acid or base. So we can also determine the Ka or Kb if the analyte is considered weak. Today, none of the acids or bases that we're going to be looking at are weak. They're just going to be strong acid, strong base titrations. So there are a couple types of titrations that are out there. Once again, the one that we're going to be looking at is a strong acid, SA, strong base, SB titration. The analyte can change in terms of its strength. However, the substance that you're titrating with, the titrant, should always be strong. So the other types are going to be a weak acid, strong base, or conversely, a weak base, strong acid. Now, as far as the strong acid, strong base goes, you could titrate either of those, and these curves look fairly similar. These processes look fairly similar to each other. Just one is going to increase the pH while the other will go ahead and decrease the pH. As far as the vocabulary goes, there's a couple things that you need to keep in mind. So first off, the equivalence point is going to be the point in which the acid is stoichiometrically equivalent. Stoichiometrically is kind of a fun word. Equivalent to the base. A lot of the acid-base titrations that we'll look at in this class are going to be monoprotic or have one hydroxide group with them, so really it's going to be 1-to-1 mole ratio. But we can do titrations with polyprotic acids or with bases that will accept more than one proton. Now, endpoint is almost the same thing as equivalence point. When we're doing titrations, we often will use an indicator, which is a substance that changes color based on pH. And the endpoint is going to be the point in the titration where the indicator changes color. Where indicator changes color. Now, this is important to define because this is not exactly the same point as the equivalence point, because we as humans have some sort of uncertainty or error to when we actually measure things. So the equivalence point is going to be exactly the point in which the base is equal to the acid or the acid is equal to the base. The endpoint is just where we observe that to happen. The analyte is of unknown concentration. We're trying to determine the concentration of it, while the titrant is known concentration. We are using this to determine the concentration of the analyte. Wonderful. So I'm going to use a lot of this vocabulary. I already have used some of this, but we're going to use a lot of this vocabulary throughout our discussion today. So let's get started. A strong acid, strong base titration. Hopefully this kind of makes a little bit of sense in terms of its title, in terms of its context. But pretty much the whole point of a strong acid, strong base titration is to determine the concentration of an unknown acid or base. Determine the concentration of an acid or base. There's almost no other point to a strong acid, strong base titration. We can use these to see if you understand some of our basic stoichiometric properties, whether this be limiting reactants or excess reactant type problems. But honestly, at the end of the day, the most important question that you should be getting from this is what is the concentration of the acid or base? Like I said, these are essentially limiting reactant problems. So you want to be able to identify which substance, which chemical runs out first, because the chemical that is left over, the excess reactant, will be used to determine the pH. So once again, the chemical that's in excess, the substance that's in excess, will be used to determine pH. These are fun extra type problems. Once again, the whole point is to determine the concentration of our base or acid. Now, something fun that kind of comes up with these are titration curves. Now, a titration curve will always plot the pH of the substance versus the volume of the titrant added. Volume of the titrant added. And this is usually going to be in milliliters, but it can be in milliliters as well. And every single one of these curves looks something along the lines of this. So, for example, if our titrant is going to be, for example, NaOH, that means we're analyzing, we're looking at an acid. So therefore, before we add any pH, the pH of the solution is going to be fairly low. It's going to be very acidic. And as we add NaOH, the pH will slowly creep up, until there's a huge spike. Now, this spike is going to represent the concentration of the NaOH taking over and the concentration of the acid that we're analyzing running out. And then it flattens out again at a pH of 12 to 14. So a couple things to note about this. First off, right here where the curve changes inflection is going to be the equivalence point. So once again, where the curve changes its concavity is going to be the equivalence point. And for a strong acid, strong base titration, for a strong acid, strong base titration, the pH at equivalence point is 7. This is not true for weak acid, strong base, or weak base, strong acid titrations, but we'll get to that later. Once again, though, the whole point of a titration curve is to plot the pH versus the volume of the titrant added. So once again, if we're looking at this, because we're representing a strong acid, strong base titration, this right here, the pH right here, is equal to 7. And this is only true because we know that this is a strong acid, strong base titration. All right, so we're gonna move along here and try a problem out and see what we can get from this. So a 35 milliliter sample of hydrochloric acid is neutralized with sodium hydroxide, NaOH. If 75 milliliters of 0.095 molar NaOH is required, what is the concentration of HCl? So first thing I want to go ahead and do is just identify what the chemical reaction is. We know that we have sodium hydroxide being added to hydrochloric acid. When this reaction occurs, we know that an acid and base reaction will produce water and the resulting salt, which in this case turns out to be table salt. We can use the molarity and volume of the sodium hydroxide, the molarity being 0.095 molar, and the volume being 75 milliliters, in order to determine the number of moles. The number of moles will be this multiplied by each other. I'll give you guys a second to do this. And don't forget to change your volume into liters, excuse me. But hopefully you go ahead and get 0.0 0.07113 moles of NaOH. Now, since HCl and NaOH are reacting in a 1-to-1 mole ratio, we can assume that the amount of moles of NaOH reacted is equal to the amount of moles of HCl that was present. So that's 0.00713 mole HCl. And we had a 35 milliliter sample. So this is going to be 0.035 liters of HCl. We take these two and divide them by each other. And we go ahead and find that the concentration of HCl is going to be roughly 0.204 molar. If we're going to do significant figures, we're using 2 sig figs. We'll go ahead and bring this down to 0.020. Excuse me, 0.20. 0.20 molar. Awesome. There's one last question here, which, as usual, I'll let you guys go ahead and try out. The solutions to this are online. What is the concentration of HCl if a 25.5 milliliter sample requires 72.3 milliliters of 0.15 molar KOH to reach equivalence? It's worded kind of differently, but it's pretty much the same type of problem. And for your fun viewing pleasure, yes, the titration meme of phenolphthalein and overshooting it. So wonderful. Hope you guys have an awesome day.